So, lesson 1, momentum and impulse. Momentum. Momentum really is the amount of motion an object has. I thought that was kinetic energy. Actually, we're talking about it in a slightly different way. In fact, here's an example. For each of the diagrams below, state whether the amount of motion is comparatively large or small. If you have a tiny object, think ping pong ball, traveling with a tiny velocity, do you think that has a large amount of motion or a small amount of motion? Would you prefer to be hit by a ping pong ball traveling slow? Sure. So let's write here small. What if you have a lightweight object, but I drew a long arrow to kind of suggest that it was traveling really fast? You know what? What's a lightweight object that travels really, really, really fast? Bullet. Okay. Do you think a bullet has a small amount of motion or a large amount of motion? Bigger. Think bullet. What about a heavy mass, a bowling ball, let's think, traveling slowly? This is also big. What would hurt worse, getting hit by a bowling ball or getting hit by a bullet? Bullet right now. The worst collisions, I didn't include it on here, are big mass, big speed, and a good example of that is a train. Getting hit by a train, you have a large mass and you have a large speed. Put the phone away. Thank you, sir. That has an awful lot of motion. In fact, the amount of motion an object has, Michael, it depends on two things. Its mass and its speed. Well, isn't that a half mv squared? That was how much kinetic energy it had. And we're talking about a slightly different concept here. So, let's do that. Explain your answer. We kind of just talked about it. Momentum depends on both mass and speed or velocity. We call it the motion product. We can't use m for momentum because m is already taken by what? What does the letter m stand for in physics already? Mass. So we go with p for product. So you're multiplying it together. Momentum is a vector quantity. Energy was a scalar, and you heard me say often last unit, one of the nice things about energy was it was very handy for curvy paths because it was a scalar. It was handy to analyze that. Momentum is not. Momentum is a vector. So there's our vector symbol, and it's equal to mass times velocity. Mass times velocity. What are the units for momentum? William, what do I measure mass in? It's after spring break, I know. Kilograms. What do I measure velocity in? Momentum is measured in kilogram meters per second. And they haven't changed that or named it. There is a movement afoot right now, and it may happen in your lifetime. They're talking about renaming this as one Einstein, because he doesn't have a unit named after him, and he is one of the big scientists as well. Hasn't happened yet, so for now, Hakeem, it's a kilogram meters per second. Careful, remember that force was a kilogram meters per second squared, because force was mass times acceleration. This is not a force. It's kilogram meters per second. But I wrote down here, note, a Newton second can also be used as a momentum unit. Say what? Let's write down here, Newton times second. Let's put an equal sign. What did newtons measure? I'm looking for one word begins with the letter F. Okay, newtons measured force, and force was what times what? mg was a specific type of a force. What was our generic equation for force? Andrew, you're right, louder. So, MA. Did you say MA? Yeah. Kilograms, A, meters per second squared. Yes? A Newton was originally a kilogram meter per second squared, and if I multiply that by another S to get Newton seconds, can you see, AJ, how many S's do I have on top? Can you see there's one up on the top there on the right? How many on the bottom? Can you see there's two? And we would then say, AJ, hey, one of these would cancel, and can you see I am left with kilogram meters per second. So you'll see some textbooks, they won't say momentum measured in kilogram meters per second. Some textbooks will say momentum is measured in Newton seconds. In fact, we're going to use both in certain situations. So let's try. I always like to try and give you an example of what's really big and really small as answers. So Perry, if you make a calculator mistake, you can like, this doesn't look right. So let's estimate some momentums. We're going to estimate in particular the momentum of top pitcher's fastball, the momentum of a person and bicycle on a relaxed ride, and the momentum of a car on a city street. And the way we're going to kind of estimate it, or the way we're going to kind of quantify it, is to ask, how much would it hurt to get hit by this? Okay? So, fastball, baseball, estimate the mass in in kilograms. Now, anybody here play baseball and actually know the mass of a baseball? No? Okay. Do you think a baseball weighs half a kilogram, or is that too high, or is that too low? No idea. Someone said too high, someone said too low. Does a baseball weigh a pound? Because that's what you guys are used to for weights. Or is it higher, or is it lower than a pound? Now I'm kind of looking at some of the guys who maybe occasionally lift weights and know how much a 5-pound weight is because they put one on a barbell and then can maybe do some rough extrapolation and say, what would about 1/5 of that weigh, and would that weigh as much as a baseball? Elijah, you're shaking your head. Do you think a baseball weighs more than a pound or less than a pound? Probably about less. I think probably considerably less. Yeah. Baseball weighs, and I'm being rough here, about 150 grams. Maybe 200, maybe 250, but I'm going to use 150. So we got to go to kilograms, so 0.15 kilograms. Okay, speed. Baseball fans, how fast does a major league pitcher pitch? The best guys, what do they top out at, or what do they approach? 100 what? I need units. Okay, 100 miles per hour. Problem is we got to go metric, but I've done physics enough to know that if you divide miles per hour by 2, that's roughly meters per second. So 100 divided by 2 is what? It's actually about 45 meters per second. So on your calculator, can you go mass times velocity and tell me what's the momentum of a major league pitcher's fastball? 6.75 units, kilogram meters per second. If you got hit by a pitcher's fastball in your torso, would it kill you? No. Would it injure you and send you to the hospital? I don't think so. It would ouch. You know what? If you have to absorb about 10 kilogram meters per second, that's ouch. That's owie. That's bruise, but that's not medical care required. Okay. Bike and rider. Next one. Let's estimate the mass. Well, what does a person weigh in kilograms, roughly, give or take? 75 kilo. You know what? Probably a little less, but let's add the mass of the bike, and 75 is a nice number. Let's say the whole mass of the bike and the rider, 75 kilograms. How fast can you go on a bike? Can you go 60 kilometers an hour? Can you do road speed on a bike? But it does say a relaxed ride. See it? It says in part B. So relaxed ride, let's put it at about half that. In fact, you know what? Let's be clever. Let's make it 36 kilometers per hour. That is a fairly relaxed bike ride. Why did I pick 36? Because how do we go from kilometers per hour to meters per second? Divide by 3.6. See why I picked the 36? This is actually 10 meters per second. You know what? Yeah, I think when you're traveling fairly relaxed on a bike, you cover about 10 meters every second. That's, I mean, you're moving, but you're not, you know, Tour de Francing, sprinting, or anything like that. So, I can do mass times velocity in my head. 75 times 10 in your head. Okay. So, you're walking on the sidewalk, you're not paying attention, or the bike rider's not paying attention, and you get hit by a biker on their bike. Will that kill you? Don't think so. Can it injure you? Yeah, you might break a limb. So 750 kilogram, about 1,000 kilogram meters per second. If your body's trying to absorb that, Matt, you're not happy. But you'll probably be able to tell a story about it afterwards. Okay. Car. What's a car weigh? Rough guess, mass. A ton, which I know what that is, but most of these people don't know the metric. What's a ton in kilograms, please? Okay, you know, 1,000. Some heavier, some lighter, but 1,000's a nice number. Speed. Let's go freeway speed. So what's the speed on the freeway in kilometers per hour? You guys are getting your licenses, or have them. You should know this. On the Trans-Canada, what's the speed? It's not 80. It's not 60. It's 100 kilometers per hour, folks. There's construction zones where they slow down, but it's 100 kilometers per hour. You know what? I'm going to be really, really clever. I'm going to go 108 kilometers per hour. Why? Can you divide that by 3.6? I think this one should also work out evenly, I think. It is? Okay. 30 meters per second. This is the momentum of an average car on the freeway. What's the momentum? 1,000 times 30, which in your head, Connor, is?
30,000.
Let me pause for a second while I deal with my late-coming miscreant. Hey, if you get hit by a car on the freeway, pain? Yes. Injury? Yeah. Terminal? Yeah, probably terminal. I mean, there are people that survive, but not likely. Okay. So this gives you an idea of what's a small amount of momentum and what's a big fatal amount of momentum. Although there is another factor involved that we're going to talk about shortly. It is very possible to absorb 30,000 kilogram meters per second of momentum. Very possible. And come out of it perfectly fine. There is another factor that we're going to talk about. Example 3. Baseball of mass. Oh! There, I did look up the mass of a baseball. 0.14 kilograms. What did I say about 0.15? Yeah, it's close. None of you looked down to figure that out when I asked earlier? Okay. Could have just read the next question and spotted it there. I knew it was there. I wanted to see who else would. I do the same song and dance every time, Matt. This is a been there, done that. Find the momentum of the baseball. Okay. Momentum is mass times velocity. And Riley, you're going to notice in this unit, I'm going to be way fussier with the vector notation. I don't take marks off if you forget vector notation, but I use this as a reminder. It's going to be direction in this unit, and especially when we do momentum in Physics 12, is going to be hugely, hugely, hugely important. And so I always remind myself, here now, unlike energy, which is a scalar, direction, direction, direction matters. Momentum is mass times velocity. It's going to be 0.14 times 35. What is 0.14 times 35? You already did it? What'd you get? 4.9. 4.9? 4.9 what? Units. Kilogram meters per second. Mr. Dewick, you said it's a vector. What's the direction? The direction would be in the same direction as the velocity, Tanisha, but whatever. B. Find the velocity at which a bowling ball of mass 7.26 kilograms would have the same momentum as a baseball. By the way, do you think the velocity will be slower or faster than a baseball? If you want the same momentum as a baseball for a bowling ball, do you think you have to throw the bowling ball faster than the baseball, or can you throw it slower than the baseball? Slower, okay? Well, one goes up, the other goes down if you want the same momentum. Momentum is dependent on mass times velocity. Oh, in fact, I think the velocity is going to be the momentum divided by the mass. Is that another equation that comes out of here? Yeah? By the way, this is one of the many reasons I taught you at the beginning of the year formula manipulation, because you don't want to memorize every single permutation of this. And those of you that are still using I humbly suggest that there are better tools than that if you just learn the algebra, because now you can do it with any equation, right? Elijah's sitting there, but I like that little triangle. Yeah, okay. We want a momentum. Was it 4.9 exactly, or do you remember what you got on your calculator, Callum?
Yes.
It was 4.9 exactly? Nice. Divided by 7.46, sorry, 7.26. How fast would you have to throw a bowling ball so that it has the same momentum as this baseball, which is moving at 35 meters per second? What did we say for the baseball? I think we put it at 40. So 45 meters per second was a major league fastball. 35 meters per second in this example, that's still, most of you can't throw that fast. What do you get?
0.67 meters per second.
Okay. Hey, turn the page. Example 3, I wrote down here, prove, or show, Dylan, that momentum change equals mass times velocity change. What word appears twice in that sentence? Begins with letter C. Change. Hey, what's change in anything? There's a reason I worked that in. What's change in anything? No, the first one was right. Not winner minus loser. That's for our tug of war analogy. Final minus initial. What's changed in anything? Say it again. So let's write that down here. So I wrote, prove that momentum change equals mass times velocity change. Well, Connor just told me that change in anything is going to be final minus initial. Right? But what did we just say momentum was on the previous page when we see the letter P, momentum? Momentum is what times what? Except I never wrote it that way. Please, in the correct order. Mass times velocity. And I think it would be reasonable, Riley, to assume that momentum final is mass times velocity final minus, and momentum initial is mass times velocity, because I don't think the mass is changing. Although it can, but we need calculus to deal with that. So I think we're going to say this on our next line. So far, so good? Perry, look at the right-hand side of this equation. There is a letter that appears in both terms. No? What letter appears in both terms? On the right-hand side, Sesame Street is brought. there's a letter that appears in both terms. It's meant to be screamingly obvious. It's in front of each term. The letter M. It's a mass. We call that in Math 10 a GCF, a greatest common factor. I could actually rewrite it like this. Right? Connor, what's changing? Anything? I'm going to reverse the question. What's final minus initial? Ah, look. Our final answer here, our final proof, isn't V final minus V initial the same as delta or change in V? Now, what was I trying to prove? I wrote prove that momentum change, which I think I would write delta P, equals mass times velocity change, which I think I would write M delta V. Have I proved it? Yeah. Okay. Why is that so important? Well, Tanisha, we're going to give a special name to change in momentum. Change in momentum is such an important concept that it's one of the only change-ins that gets its own unique name. Can you guess what name it gets? Ah, Matt, very good. See, this reading down, looking ahead thing does work. After all, what do we call change in momentum? Impulse is defined as change in momentum. When you see the phrase change in momentum, McKenna, you can think to yourself impulse. When you see the word impulse, McKenna, you can think to yourself change in momentum. Oh, and when you think for both of them, change in momentum, what you're really also thinking is it's going to be the mass times the change in velocity. Final minus initial. By the way, I think this is, someone have their yellow formula sheet handy? I think this is the equation that I gave you, although almost always I jump straight to this second line here because I usually just go MV final minus MV initial instead of using brackets and stuff. Is that on there at all? That's a whole different one as well. Yeah, what we're gonna start to do now is we want to try and relate momentum to force. So I wrote here example 4. Fill in the steps below to find the impulse equation. Take Newton's second law, F net equals ma, and solve for acceleration. So I have F equals ma, get the a by itself. F over m. Sure. Oh, and then take the kinematics equation V final equals V initial plus AT, and also solve for acceleration. Get the a by itself. So we did this, holy smokes, like in October, a while ago. Happy Halloween. V final equals V initial plus AT. You guys were good at this once. Get the a by itself in that one. A equals, do you remember? Or can you redo it in your head? Uh-oh, here's my pen stopped working now. Well, while we're waiting, anybody? Let's try doing that. Time out whilst I figure out my tech issue. So humans, if I give you, I really want that ribbon display options, show ribbon, and then I do that. If I give you V final equals V initial plus AT, get the a by itself. Yeah. Ah, Connors, look at him in the front row. I'm almost willing, the whole late, I could almost, go ahead. V final minus V initial over T. Remember that? Remember? So you ready? What does F over M equal? What does VF minus VI over T equal? So if they both equal acceleration, can I not just say they both equal each other? Ah, here's how we're generating our new equation. We're going to say F over m equals v final minus v initial over t. So AJ, you have your formula sheet in front of you. You may see where we're going here, because I wrote then cross multiply. We're going to move the t up diagonally. We're going to move the m up diagonally. We're going to get this. Change colors, Mr. Duick. F times t equals, and hang on. I'm going to write m, but instead of writing v final minus v initial, what is final minus initial? I'm going to go like this. This is the impulse equation. Although I might have a delta. Do I have a delta in front of the t on your formula sheet? That's to make it look symmetrical, but time was always a change in anyways, but yeah. You want to find the impulse on an object? There's two ways to figure it out. If you know the mass of the object, its final velocity, and its initial velocity, that's the impulse. Or if you know the force that was applied to the object and how long that force was applied to the object for, that's another way. This is our equation for the day. Oh, I wrote here, substitute result of example 3. We did that on the previous line. So here's our equation. Really? Going to do it again? See if it'll come back now. No, it didn't. Come on, pen. Okay, this is going to be a problem. I may have to go back to the old system. So here's our equation. Oh, come back here. F times change in time equals mass times change in velocity, and both of these equal, make that a proper letter P, Mr. Duke, change in momentum, which is also called impulse. Is also called impulse. I wrote down here, you may have noticed that we seem to be paying more attention to vector notation than we have been for the past few lessons. It is true. This is because in momentum problems there are often changes in direction. And so we need to use precise vector analysis like we did for velocity and acceleration. We need to let up be positive and down be negative, or to the right be positive and to the left be negative, or forward be positive and backwards be negative. Example 2. A .144 kilogram baseball, oh, I'm getting more accurate with my baseball mass, is pitched horizontally at 38 meters per second. After it's hit by the bat, it moves in the opposite direction at 55 meters per second. How do I know in the opposite direction? Because I put a negative in front of it. A, what impulse, what's another word for impulse? What change in momentum did the bat deliver to the ball? Well, right now I sort of have, Matt, two equations for change in momentum. I have force times time, and I have mass times change in velocity. Look at the equation. Look at the information, I'm sorry, that they gave you. Look at the question. Do you think I'm going to use force times change in velocity, or force times change in time, or am I going to use mass times change in velocity? What information did they give me? A mass, and they gave me 2 velocity? Okay, I'm going to use this one. Except I usually write this as mass V final minus mass V initial. Yep. What's the mass? What's the final velocity? Negative 55 minus mass 0.144. What's the incoming initial velocity? 38. What is the change in momentum on this baseball? I get negative 13.4. Anybody else? Kilogram meters per second. What's that negative mean? It does not mean last unit when you got a negative energy, that meant that it had lost energy. That's not what it's saying. It's saying the change in momentum was in the negative outgoing direction. Sorry? 0.4? 0.4, Mr. Dewick, thank you. Let's try that again. 13.9, we'll make that 13.4. But that negative is saying, not that you lost momentum, it's saying that you had positive forward momentum and you left with lots of negative backwards momentum. Your change in momentum was in the opposite direction. B. If the bat and the ball were in contact for 0.8 milliseconds, now let's make a little note here, 0.8 milliseconds, that's actually 0.8 times 10 to the negative 3 seconds. Because I think milli is 10 to the negative 3 if you look at your formula sheet. I think I got that one memorized. So if the bat and the ball were in contact for 0.8 milliseconds, what was the average force the bat exerted on the ball? What does this question want me to find? What does B want me to find? Force. Hey, do I have an impulse equation that has force in it? Ah. Another way to write impulse, Matt, my friend, is that. Now, they want me to find the force. Matt, how would I get the force by itself? By? I agree. The force is going to be the change in momentum, the impulse, divided by the time. Did they give me the time? Yeah. 0.8 times 10 to the negative 3, 0.8 milliseconds. Did they give me the delta P, the change in momentum? Hey, what's another word for change in momentum? Impulse. Oh, we just calculated it in part A. Yes? Negative, and I'll use the full value, 13.392. So this divided by 0.8 times 10 to the negative 3. And I get negative 16,700 newtons. What's the negative telling me? The direction of the force was in the same direction as the change in momentum. You applied a force in the opposite direction of the pitch coming in, which makes sense. I've seen enough baseball. C. What's C asking me to find? Average acceleration. What did we just find in part B? Force. Oh! Yeah? Do I know the force? Negative 16,740. Do I know the mass? divided by 0.144. Average acceleration, negative 116,000. That's a pretty good acceleration. Negative 116,000 meters per, negative 116,000 meters per second squared. I'll go to 3 sig figs. Now, Riley, there is another way we could have found the acceleration. We could have said, I know V initial, see it? I know V final, see it? I know T, and I could have gone V final minus V initial over T and found A. But I was also able to get there using impulse and momentum. Well, why would you do it that way? Well, patience. Who's my football players? Let's look at a little football. What's the momentum of a 112 kilogram football player running with a speed of 3.6 meters per second? Well, momentum is mass times velocity. (112) times 3.6 . 403 kilogram meters per second. I think we said 1,000, if it hit you, would do you some injury. That was the bike rider on a bike, right? Okay. What impulse must a tackler impart to the football player to bring him to a stop? Well, impulse is change in momentum. What's change in anything? If I want to bring him to a stop, what do I want his final momentum to be? 0. Minus. Oh, and what's his initial momentum, Tanisha? We figured it out in part A. 403. Right? So if I'm going to tackle this guy head on and bring him to a stop, I need to apply an impulse of negative 403 kilogram meters per second. So far, so good. Suppose the tackle was completed in 0.8 seconds. What average force did the tackler exert? What are they asking me to find in this question, Amanda? Force. And what other information did they give me? I can also then say another way to think about impulse is force times time. And Tanisha, did we just figure out the impulse in part B? This is where we can use both the equations. The fact that impulse is change in momentum, it's how it's defined. Final minus initial. But it's also force times time. We can flip-flop between the two and find whatever's missing if they give us enough information. So if I want to find the force, that's going to be equal to the change in momentum divided by the time, which is going to be negative 403, what was it, 0.2, divided by 0.8. Negative 403.2 divided by 0.8. I get a net force of negative 504 newtons. And again, what's the negative telling me here? It's not a loss of force. That's a direction. It's a vector quantity. It's saying the negative is in the opposite direction that the runner was running, which makes sense. I don't bring a runner to a stop by pushing him forwards. I bring a runner to a stop by applying a force backwards. Then I wrote here, although we solved the previous problem using impulse, we really could have done it using Newton's laws. So why do we bother with momentum and impulse? Tara, the main reason is momentum is the best tool that we have to analyze collision problems. That's next lesson. We'll start looking at car crashes. There are, however, a few questions that are most easily answered using impulse. For example, consider the following. Example 6. 2 eggs are dropped from a height h. One hits the floor and breaks, and I wrote splut. The second falls into a pail of water and survives. What's the main reason the second egg survives? I want you to notice something. Do both eggs have the same mass? Yes or no? Yes? Do both eggs have the same initial velocity? What is it, by the way? 0. If they both drop the same distance, will they both hit the ground at the same velocity? You know what this means? Riley, this means, what do 3 dots mean? Therefore, they both undergo the same change in momentum. They both undergo the same impulse. So why does one break? Why does one not break? Andrew, what?
Because there's more time for the egg to stop in the water, there's less forces in the company.
Ah. Yeah, whose phone was that? Leave it off. So Andrew, if I heard you correctly, you're saying, Mr. Dewick, impulse is equal to force times time. Is that what you're saying? Say yes. Because they both have the same impulse, we're stuck with that. Okay? How can I make the force smaller? As time of collision gets bigger, force gets smaller. So I've had enough of Zach. So I agree with Andrew's answer. Let's, you know what? Let's see. Here's how I think we'll write this. So let's go ground, water. Drop the egg into the pail because they both, Dylan, you agree with me? They both undergo the same change in momentum. They have to because they both have an initial, when they hit the ground of whatever V final is, and their final speed is 0, they both go through the same change in momentum. On the ground, we have this. Big force, small time of collision. In the pail, we have this. Small force, way bigger time of collision. Is that a short way to write that? That we'll know what that means? Okay. That's what football pads are trying to do, by the way, as well. Well, football pads, Callum, are trying to do 2 things. They're trying to lengthen the time of collision, and they're trying to spread the energy out over a wider surface area as well. I wrote down, here's another way to think about the egg question. Why do they use bales of hay to line some racetracks? What's the advantage in being brought to a stop by a bale of hay instead of a brick wall? Explain your answer in terms of impulses and forces. So I would argue, if you're running into a brick wall or you're running into a bale of hay, your change in momentum, Zach, is the same no matter what, because your final momentum is 0 in both situations, and let's assume your final velocity is 0 in both situations. Let's assume your initial velocity is whatever the racetrack speed is in both situations. So your change in momentum is the same in both situations. What can we change? Again, we can make time bigger, force smaller, or we can make time very small, force really big. It's not the time that kills you, it's the force that kills you. Next page. Example 7, I wrote down, in many sports that involve striking something, tennis, baseball, soccer, golf, hockey, etc., players are told to follow through when they come in contact with the ball. Why might this help the ball leave with a greater velocity? What? Perry. You're right. What?
Longer contact.
Instead of longer, let's go back here. Which which variable are you affecting by following through with a longer contact? I kind of gave it away. Time. So by following through, even if you have the same force, but if you can increase the delta T, even double it just slightly, you get a bigger impulse, a bigger change in momentum. Who's played tennis? Anybody of you? How do you do a drop shot? What do you do? No, a drop, like, you know what I mean by a drop shot, right? Where you want to just drop it over the net? What do you do? Or who plays baseball? Who's played baseball? How do you bunt? Not only do you not swing all the way, as a matter of fact, what you try and do is pull back on the impact as well. You really try and minimize the delta T. On a drop shot, what you're trying to do is pull back as you hit it. Actually, if you time it just right, you can maybe have it go about 6 inches and drop like a rock. Watch the pros; they can really do it really, really well. And you can put spin and all sorts of stuff on it as well, but that's more complicated than the physics we're looking at right now. But in all of those, you're trying to reduce your delta T because you don't want it to go very far. Which has more momentum? A 1,000-kilogram car moving at 100 kilometers per hour, or a 2,000-kilogram truck moving at 50 kilometers per hour? Ah! Even if we don't convert the units, they're the same. So getting hit by a slow-moving truck or a fast-moving car would do the same amount of damage to you. The worst collisions are when you have something really heavy and really fast. And sorry to get a little morbid, but this is the Twin Towers. You had heavy planes traveling really, really fast. You're going to learn, Dylan, in the next couple of lessons that momentum, like energy is conserved, momentum has to go somewhere too, and the buildings could not absorb the momentum. That's why they came down. It's why when locomotives hit something, there is so much damage, because those have a pretty huge mass and they're moving pretty fast as well. Hey, it's why an asteroid is going to do a lot of damage if it ever does hit the Earth. High mass, high velocity, that momentum's got to go somewhere. The Earth will try and absorb it. Well, it'll do some damage. Does a moving object have momentum? Does a moving object have impulse? What did we say impulse was? Only if V is changing. Right? If it's at a constant speed, Tara, then we would say it's got momentum, but there's no change in momentum, no change in delta V. Constant speed, no impulse. If you were to jump from your lab table to the ground, or all of you at least once have been at a playground as a kid, and you jump from the playground, whatever the crappy, lousy playgrounds that your generation has, risers that are only about that high, and you jump down to the ground. Or my generation, where we had playgrounds that were taller than you, and you could actually hurt yourself and die on them, but they were great playgrounds. But regardless, when you jump from a high height down to the ground, why do you bend your knees as you land? Ah! You're lengthening the time of impact. It's the same as the foam did for the baseball bat when I schmucked Zach upside the head. You okay, Zach, by the way? What was that? There has to be something to damn it? Oh, yeah, okay, fair enough. Example 12. Which of the following situations is more likely to knock out a boxer? So a boxer is going to absorb a punch. In the first situation, he moves back to absorb the punch. The fist still comes to a stop, so the change momentum on the fist is still the same. In the second situation, he doesn't move back to absorb the punch, he just tries to stop the punch. Which one is more likely to knock out a boxer? B. Why? It's the same change of momentum. What are we changing?
Short one.
We're changing the time, which leads to a change in the force. If it's got to absorb the same amount of momentum, if you have a shorter time of impact, okay, the force is going to go way up. It's going to go way up. Is that okay? Okay.